Greetings and welcome to another news installment for the ICQ YouTube channel. We aim generally to issue these news videos bi-monthly, with alternate bi-monthly videos issued containing interviews with comet, meteor, and small solar system bodies specialists. However, though we have maintained our interview video schedule this year, this is the first of our news videos since early April, so we have some catching up to do. It has been an interesting half year. In addition to the frequent discoveries of new faint comets and general faint recovered comets, we have had a bright-ish comet discovered this past month by amateur astronomer Hideo Nishimura from Japan, designated as Comet C 2023P1. Nishimura found the comet at around 10th magnitude on August 12th using a digital camera with a 200mm focal length telephoto lens. But it was close to the sun in the morning sky and had been close to the sun's glare for many months, explaining why it was not discovered by any of the big surveys. Pre-discovery images of Comet 2023P1 were found later by Rob Warwick on images taken last January with the 1.8-meter Pan-STARRS telescopes in Hawaii, when the comet was very faint and essentially stellar in appearance, showing no cometary activity then. Warwick's observations allowed us to calculate that the comet orbits the sun once every 437 years approximately, so that it was last close to the sun perhaps in July of 1588. Intrinsically, the comet is not particularly bright or large, but it has been brightening as it nears the sun, currently visible in good binoculars in the morning sky as dawn is beginning, with the comet rising in the east if you know where to look. Photographically, as shown in images here that have been posted at our ICQ Comets Observations Facebook forum, Comet 2023P1 has shown the greenish coma typical in comets this bright due to ionized carbon in the comet's head, along with a rather thin ion or gas tail that has grown to 2 degrees or more in length. Visually, gas tails are very hard to see, so it looks more like a colorless round diffuse object with a central condensation through a small telescope or binoculars. But long exposure photographs bring out detail that the human eye cannot see directly. The comet should continue to brighten as it nears its perihelion or closest approach to the sun on September 17th, afternoon universal time, or at 0.225 astronomical units from the sun, or about 34 million kilometers or 21 million miles from the sun's surface. However, the comet will be only 12 to 14 degrees from the sun during the week before and a few weeks after perihelion, so it is not likely to be visible even in binoculars at a peak total visual brightness expected to be around 3rd magnitude when so close to the sun like that. A hope was that it might develop a nice long bright tail that might be visible in a darker sky with the comet's head below the horizon, but this appears to be a very gassy comet with very little dust shown. And as noted a minute ago, gas tails are very difficult to see visually. It is highly unlikely that this comet will ever be seen via naked eye because of its proximity to the sun in the sky. Perhaps the comet getting the second most attention in the last 6 months has been Comet 12P Pons Brooks, which underwent a large outburst in brightness in mid-July and showed a most interesting expanding coma similar to that seen in Comet 29P during its frequent outbursts. Comet 12P has a 71-year orbital period and may reach faint naked eye brightness next April, with perihelion then occurring somewhat inside the Earth's orbit at 0.78 AU from the sun. Another recently recovered intermediate period comet is 13P Olbers, not seen since 1956, and also having an orbital period around 70 years. It may reach 7th or 8th magnitude near perihelion next June 30th, but its perihelion occurs somewhat outside the Earth's orbit. Mike Meyer and Gary Kronk have just published Volume 1 of their Catalog of Unconfirmed Comets, covering the years 1600 to 1899. Out of their work, they identified additional observations for 2 comets that have now been formally designated and named this past May. One was found in 1954 by Ingrid Grunewald on plates taken in 1951 on only a single night, and another single-night discovery from Palomar Sky Survey plates obtained on a single night in 1952, but again not found until many years later. Detective work by Meyer and Cronk led them to identifying several other nights of observations in 1950 and 1951 to link the 1951 and 1952 comets as a single comet. Another interesting find by Meyer and Cronk was additional observations in manuscript letters in a library in Göttingen, Germany, of an unconfirmed comet found by Jean-Louis Pons in September 1808. These additional observations allowed a reasonable orbit to be computed from a week-long arc, or from approximate positions by Pons. The comet is now designated 1808 R1 and is the 27th comet named for Pons, the all-time visual comet discoverer. We plan to post another news video in November. Meanwhile, I now turn the video over to our new team member, Kacper Wierzchos, who has put together a short presentation on so-called Centaur minor planets in the region of the outer major planets of our solar system, many of which have been found to show cometary activity in the last several decades.
Greetings, this is Kacper Wierzchos with the ICQ Comets and Cousins channel. Today I'm here to start a new educational series of videos with topics related to comets. In this first episode, I'm going to talk about the active centaurs. Let's start with some definitions. So what is a centaur? In general, a centaur is a body in the solar system whose orbit ranges between Jupiter and Neptune, has small orbital inclination, and may be in transition between the inner and outer solar system. Due to their gravitational interactions with the giant planets, most notably Jupiter, centaurs have orbits that are not very stable, and thus their dynamic lifetimes in the Centaur region tend to be relatively short. In astronomical terms, that is, in the order of a few millions of years. It's important to note that due to their dynamic transitional nature, there are different definitions of what a centaur is. And for example, some people consider comet 29P Schwarzmann-Wachmann to be a centaur, while some other authors consider it to be a Jupiter family comet. Centaurs can have characteristics of both asteroids and comets, and thus they are typically named after centaurs, that is, the mythological creatures which are half horse and half human. In 2019, my colleague Galsarit proposed a new mechanism in which centaurs migrate to the inner solar system and become Jupiter family comets through what he called the gateway region. This gateway region is an area in the orbital element space defined by having a perihelion distance larger than 5.4 astronomical units and an aphelion smaller than 7.8 astronomical units. There are currently 4 known centaurs in this gateway region, and 3 of which are actually comets. They have cometary designations, and of course they have been observed to be active. Numerical simulations by Galsarit and his collaborators suggest that centaurs that go through these gateway regions are the source of more than 2/3 of all known Jupiter family comets. In other words, this gateway region is a cradle of periodic comets in the inner solar system. As a comet approaches the Sun, the solar flux hits its nucleus and volatiles are released in higher quantities, peaking at perihelion. But some centaurs have large perihelia, and some exhibit cometary activity at large heliocentric distances where the solar flux is insufficient to sustain sublimation of water ice, which is the main driver of activity at small heliocentric distances. Currently, there are 42 centaurs that exhibit cometary activity and that have a cometary designation, and that is roughly 5 to 10% of the known centaur population, depending on which definition of centaur we use. So what causes centaurs to be active far away from the Sun? Well, first off, we know that solar flux is responsible for activity in centaurs. In 2009, David Jewett found that active centaurs have smaller perihelia than inactive centaurs. It is currently thought that activity in this object is caused by a phase transition of amorphous water ice accompanied by the release of trapped highly volatile molecules like carbon monoxide. Amorphous water ice is a metastable form of water ice, and when the solar flux is enough to warm it up, it undergoes a phase transition into crystalline water ice. This reaction is exothermic, and thus it can warm the surface and subsurface nuclear layers of the object where highly volatile ices such as carbon monoxide are thought to be trapped. I'm now going to talk a bit about the centers in which carbon monoxide has been detected. So as I said, CO is much more volatile than water ice. And so far this molecule has been observed in 3 active centers. Those are 174p Echeclus, 95p Chiron, and 29p Schwarzmann-Wachmann, this last one being in the aforementioned gateway region. Due to its high volatility, carbon monoxide can sublimate at very large heliocentric distances well beyond the center region. But carbon monoxide is unlikely to be sublimating freely from the nuclei of active centers and be the sole driver of activity. This is because, due to its volatility, we would be able to observe active centers as far away as the Kacper belt. But this is not the case. Rather, centers tend to be active near the orbit of Jupiter. It is interesting to note that of the 3 centers in which carbon monoxide has been found, 29p Schwarzmann-Wachmann is a carbon monoxide-rich object, whereas the amount of carbon monoxide observed in Chiron and Echeclus is much smaller than 29p. Both Chiron and Echeclus outburst only rarely, sometimes with years between outbursts, whereas 29p Schwarzmann-Wachmann has multiple outbursts per year. Echeclus and Chiron may have had more carbon monoxide in the past and substantially devolatilized after moving into their current center orbits. Active centers are a very diverse group of bodies in the solar system. Some of them are barely active, while others are constantly active. Some of them undergo massive outbursts, while others have only been observed to be active during an outburst. Further observations and modeling of these objects could provide important clues to the bulk properties of their nuclei and place powerful constraints to solar system models. I hope you enjoyed this short introduction to our active centers, and I'll see you in the next one. Take care.